Good morning. We are Group 57, also known as ML Dogs, and this is our SC4000 project presentation. Today, we'll start with the project overview, then walk through our data analysis and preparation. After that, we'll cover the models we built, our results, and our key findings before concluding. The challenge was ambitious: improve standard smartphone GPS accuracy from several meters down to the sub-meter level. We were given raw GNSS and motion sensor data from Android phones with the goal of building an algorithm for highly precise location tracking. The impact of this is enabling new applications like accurately detecting which lane a car is in. This required techniques like sensor fusion and outlier removal. Over 1,300 teams competed, creating a strong public benchmark for this research. Our success was measured by the distance error against the ground truth. Our first step was a deep dive into the data, known as exploratory data analysis or EDA. We found the data was highly heterogeneous, organized by different drives and phone models. A major initial hurdle was discovering multiple timestamp formats that all had to be perfectly converted and synchronized. Data quality was our biggest challenge. The GPS and motion sensors had a massive sampling mismatch. We also found significant data gaps and missing values. In short, the data set was sparse, noisy, and inconsistent. Our key takeaway was clear. The variable signal quality and missing data meant this problem could only be solved with extremely strong preprocessing. So that led us to our preprocessing phase. We built a pipeline to manage this. First, we standardized everything into a unified schema and normalized the timestamps. Then we extracted features from the raw GNSS signals, the GNSS status, and the IMU motion data. Critically, we also generated our own high-precision baseline using PPK processing. Finally, we fuse all these new features, aligning them with a 50 millisecond window and adding rolling statistics. We use DAS to process this in parallel, resulting in a single featureized CSV file with non-coherent data. It was largely because our pipeline code was majorly created by Gen AI, which led to a lot of faulty logic. This led us to make a more systematic approach of using source codes and academic papers to our advantage. Now, before we could even think about machine learning, we had to solve a fundamental data problem. A standard smartphone's GPS is incredibly noisy, with errors often exceeding 10 meters due to atmospheric delays and clock drift. Our entire strategy was built on post-processing kinematics, or PPK. The key insight is that a nearby base station experiences the exact same atmospheric noise. We use an open source tool called RTKlib to take the data from our phone and the base station and essentially subtract this shared error. This cancels the noise and lets us use the hyper-precise carrier phase, or ADR, for positioning. To do this, we built a hybrid pipeline. We use Python to orchestrate the workflow, while the original C executables from RTKlib handle the high-speed computation. This pipeline had to automatically fetch two external datasets, satellite navigation files and the base station data. This is where we primarily hit our first wall. The download links for the nav files were broken, returning error 404s. So we had to reroute our script to a more reliable archive. Even worse, the base station data would sometimes fail to download silently. We had to build in explicit error handling to catch these failures before they corrupted our data. Our first attempts were a complete failure. The initial run failed to lock onto the precise carrier phase and was forced to use the noisy pseudo-range data. The result was catastrophic, with errors from 100 to 1,200 meters. Our final method was the breakthrough. By correcting our configuration, we successfully enabled differential cancellation. This eliminated those dangerous outliers. We had one last bug. Our comparison script kept failing because RTKlib's time format was incompatible with Unix timestamps, which we fixed with a robust parser. The results show the full story. The before plot on the left shows our initial 2.5 meter median error. After our PPK solution, we achieved a 1.24 median error. This new high fidelity baseline is what gave us our 3.004 Kaggle score. This was the most critical step of our project. We successfully transformed raw, unusable data into a high precision data set. This became the essential foundation for our machine learning model.
We split the data 80-20% based using a scikit-learn. We use the 80% for training and 20% for validation. This ensures that there's a balanced learning while preventing overfitting. Model approach. Our first approach was a dual strategy. We began by tuning a LGBM light GBM model, which served as a strong baseline. In parallel, we developed a sophisticated neural network with a custom Gaussian NLL loss function. This was designed to predict not just the position correction, but also its uncertainty, which we then fed into Kalman filter. Model results and hybrid experimentation. However, despite its complexity, this neural network and even the hybrid model combined it with the LGBM failed to outperform our baseline. The key takeaway was that complex architecture wasn't adding significant value. This forced us to pivot. Instead of building more complex model, we asked what the model wasn't the problem, but the features were. So then that's where we went for our approach too. Here, after our approach showed that there was a big limitation, we thought position error in GNS actually follow physical motion laws. So instead of building more complex neural networks, we focused on physics-driven feature engineering. Our goal in this second approach was to capture subtle motion dynamics and improve generalization using LGBM combined with K-fold validation and Optuna tuning. Next is feature engineering. We expanded our feature set from 72 to over 150 carefully designed features. The base feature captured essential motion signals like velocity, acceleration, jerk, and PPK quality. We then added more advanced features such as uncertain weight position, signal composition, physics violation detectors, and multi-scale velocity patterns. But the breakthrough came from the high-order kinematic features, snap, crackle, curvature dynamics, and interaction terms. These features help the model understand very fine changes in motion, like the start of a turn or sudden GPS disturbances, which gave us the biggest performance jump, around 15 to 20% improvement compared to using basic features alone. Model, group K-fold plus Optuna plus ensemble. So to make sure our results were realistic, we trained our model using K-fold group K-fold based by drive ID. This was essential to prevent leakage. Otherwise, the model would see parts of the same drive during training and validation. Next, we used Optina to tune our LGBM hyperparameters. We ran 35 trials over 5 folds, which is 175 model training, to identify the best combination of tree depth, learning rate, and regularization. Finally, using these optimized settings, we trained a 10 model ensemble, 5 for latitude and 5 for longitude, using standardized feature and separate models per coordinate. Key takeaway. High order features were the main performance boosters, improving results by 15 to 20%. Group K-fold gave us realistic validation scores and prevented overfitting. We also learned that ML can refine PPK output, but it cannot overcome fundamental hardware or PPK quality limit. And overall, physics-based domain-aware features clearly outperform complex neural networks. This approach ultimately gave us stable improvement and ranked us in the top 10 of the competition. Conclusion. So for our final Kaggle score, we got of 2.584 meter accuracy. And for the private, we got 1.973. And the final Kaggle public leaderboard, we got 58 out of 537. And for the private, even higher, something around 30. Next, lessons learned. We learned that increased model complexity is not always meaningful. Understanding the physics behind GNS signal gave us far better results. We realized that proper validation is essential. Without group K-fold, we would have trusted over optimistic scores and which did not represent real-world performance. We learned that machine learning can only refine PPK output, not overcome limitations from smartphone, hardware, or satellite geometry. We also learned not to rely heavily on AI alone. Domain knowledge and physics-based reasoning contribute more to our performance than complex neural networks. We learned the importance of reviewing past research and established GNSS methods to ensure we were going in the right direction instead of experimenting blindly. Overall, we became more systematic, focusing on good feature validation method and realistic expectation rather than chasing model complexity. Thank you.